Hello everyone, welcome to the sixth lecture in this series. In this lecture, we are going to study two other operations on array ADT, namely searching and sorting operation. We are going to focus our attention to bubble sort alone with respect to sorting algorithms, as we have plenty of sorting algorithms. We are just going to study how sorting with bubble sort could be done with arrays. And then we will be studying about linear search and binary search with examples first and then the algorithm. So, this is going to be the organization of this presentation. First, we will study what searching is, and then we will be seeing a linear search, or in some books you might have seen it is being given as sequential search. We will see with an example and the algorithm. Then we will be studying about binary search, an example and algorithm. Then we move on to sorting operation, and in specific what bubble sort is with an example and algorithm. And I have given some review questions, and finally we will be seeing the summary. First is with respect to searching. So, searching operation means given an array with say n elements, we are going to find out the target element is present or not in that array, and if suppose the target element is present, we are supposed to report the location of the target element. And the searching algorithms broadly are of two types. One is sequential search or linear search, and the other one is binary search. We will be using sequential search algorithm when the array or the list we are having is unsorted in nature. And in some cases, if suppose only the array is of small size, or suppose if we want to make a search for a few elements, then it is advisable to go for sequential search. For a binary search to happen, there is a prerequisite that the list or the array has to be ordered or sorted at first. Only if the array is sorted, we can make an attempt to do a binary search on that array. And the advantage of binary search is that when we talk of time complexity, in case of binary search, it would be it would take very less time when compared to sequential search. So, if we have more number of elements in which we may have to find the target element, it is advisable that we go with the binary search. So, now we will be studying about both the searches in detail. So, this is the concept of searching. You are given with an array. So, in this example, as you see, you have some 12 elements starting from a of 0 to a of 11, and we are supposed to find the target element, which is 62 in our case. So, in order to do searching, what we do is we attempt to find whether 62 is present in this array. If suppose it is present, then we will be reporting its location. In this case, it is 4. If suppose we have more than one occurrence of 62 in this array, we will be reporting its first occurrence as output or the result of searching. So, this is the principle behind linear search. So, it is the simplest of all the search algorithms we have. In order to do a linear or a sequential search, we do make a sequential scan from the beginning till the end by comparing every element in that array with that of the search element or the target. And if suppose we are able to find the target in that array, we will be reporting its position or index, and that would be the result of doing a linear search. At times we may end up with reaching the end of the array, but the target element is not found in that array. In such a case, we will report that the target element is not found in the array. So, when we talk of time complexity of doing a linear search, we say it is order of n. I hope by this time you remember how to compute the time complexity, as in the previous lecture we learned how to measure time complexity as a factor of the step size in that algorithm. Accordingly, we say that the search time or the time complexity for linear search is order of n. And linear search is flexible in the way that we can apply linear search either in a sorted array or in an unsorted array. but in case of binary search there is a prerequisite that the array has to be sorted or ordered before doing a search operation. So, here I have given you an example where we do sequential or linear search on an array of elements, and you could see here initially we have an array and that array is unsorted or unordered in nature. Our target is 62. So, how we do linear search here is that we begin our search operation from the first position in that array, or we say that we do a scan from the first position in that array. I make a check whether the target is present there in the first position. So, my target is 62. I make a comparison here whether 62 is equivalent to the element at the first position, which is A of 0. Here the search, the comparison turns out to be false. 62 is not equal to false, not equal to 4. So, I may have to advance my scan by one position. So, now I advance by one position, and so now my index is 1. I now make a comparison whether target is in that location. In our case 62 is not equivalent to 21. So, I may have to advance by one position in that array, and so now my index is 2. I make a check whether target 62 is present at index 2 in that array. It is also false. So, again I advance by one position, and now I check for index 3. There also I am unable to find 62 there, just because the element there is 14. So, the comparison turned out to be false, and finally I move to the next position, which is index 4, where you could see that there is an exact match of the target. So, I report that the element 62 is present at the 4th index in that array. So, similarly we can do for one more time how the result of unsuccessful search would be in the unordered list. So, here in this case I have set up my target to be 72. You could see in the very first look 72 is nowhere present in this array, but as principle, in order to do a linear search you may have to start your scan from index 0. So, every time, as we did before, we make a comparison of the target element with the actual element in the respective index. We check whether they both are equal. If not equal, we will keep on advancing the position by 1. So, you could see that we have made several comparisons here, and at one point of time we have even reached the end of that list, but we were unable to find the target. So, it is where we stop this search operation. At this point we will report that the target element is not found in that list. So, this is the routine which we could use for doing a linear search. We have some 4 arguments here. One of the arguments is the actual array, and here we have and the first position in that array, and we have given the last position in that array, which means its size, and then we have given the search element, which is the key. We are going to look for this key in the given array, and if found we will be reporting its location or position or index. So, here we have a loop to do that scan. So, we start from first, we go up to last. So, it is I equal to first to I less than or equal to last, and every time we increment by 1. So, at every position in that array, what I am doing is I am actually making a check of whether the element at the set position in that array is equivalent to the key which I have been given as input. If so, then I have to return the position of that element, and once we will be keeping on doing this thing till we reach the last position in that array. And if in case we are unable to return the position of that element, then it means that we have not, the particular target element is not present in that array, and in that case we will be returning a value of -1. If suppose the element is available at some position between first and last, we would have returned by this time. If we have 2 occurrence of the same element in the array, then whatever occurrence is first would be returned. If there is no match, then nowhere we would have returned, and so we will be returning a value of -1 at the end, and this could be captured by the main program, and I can say that if value returned is -1, then I could display to the user that the particular element is not found in the list. So, this is how we perform linear search. So, when we talk of complexity, if suppose the search element is the lost, then we say that that is going to be the worst case. If the element is not at all found in that list, if the target element is not at all found in that list, in that case also we will be scanning from beginning till n. So, in both cases your complexity would be order of n. If suppose the element to be searched is found in the first position of the array, then we can say that its complexity is order of 1, and that is going to be the best case for linear search. So, average case would be the element available at any other position apart from first and last, and the worst case would be finding the element at the last position or nowhere the element is present in that list. Now, we move on to the next search algorithm, namely binary search. So, for doing a binary search, there is a condition or a prerequisite. It necessitates the array to be ordered or sorted. So, we can initiate a binary search only if the array is ordered. So, these are the steps which are part of a binary search, which I have shown in the form of a flowchart as well as an algorithm. So, here initially we read the array and the value to be searched in that array, and now we compute the length of the array first, which is preserved in the variable n, and then we have a variable named beginning which marks the beginning of the array. We have a variable named end which marks the end of the array, which is n minus 1. So, here our elements are actually in the array between 0 to n minus 1, and we have a variable named result which has been initialized with the value of -1. So, what we do is we iterate from beginning till end. So, we have a loop to check whether the beginning is always less than or equal to end, and if so, we compute the mid position in that array. So, mid position will be always big plus end by 2. So, thereby we compute the mid position, and then what we do is we check the element found in the mid position and we make a comparison of that element to the key which we are going to search for in that list. If suppose the mid element at the mid position is less than or equal to the key, then we say that we are going to restrict our search only to the if mid is less than equal to x, then we are going to restrict our search to only one half of the list. In our case, what we are going to do is we are going to set beginning to be mid plus 1 and result to be mid. If suppose this condition is false, then we are going to revise end to be end is equal to mid minus 1. So, if this condition is false, we are going to search the first half of the elements in that array. If the condition is true, then we are going to search the second half of the list. So, thereby with binary search, the advantage is that during every iteration the search space would get reduced to half, and thereby the search time will also be drastically reduced when compared to linear search, and this turns out to be the advantage of binary search over linear search, and we may have to repeat this process till we reach up with one element, and of course, if that element is what the key is, we will be reporting its position. If not, we will be saying that the particular element is not found in that list. So, here I have given you the algorithm. Of course, I hope you will be better understanding the concept of binary search with this algorithm. So, as I said before, we mark the beginning and end of the array with low and high. So, we will check whether low is always less than or equal to high. This is we do this step just because I told you every time the search space is going to get reduced by half, and so we check whether low is always less than or equal to high first. So, if this condition is true, we are going to repeat the steps from 4 to 6. So, we compute the mid is given by low plus high by 2, and then we compare the element with the middle element. If suppose both are one and the same, then we are going to report the position of the mid element as the index of the element found, and finally, we are going to return to step 7. If suppose the element the key is not equivalent to the mid element at the mid position, then we may have to break down the array into two halves, and we will be restricting our attention to either one of the halves. For doing so, we check whether element is less than the middle element, and if it is less, then we will be restricting our further search to the first half of that list. And if suppose element is greater than the middle element, then we may have to restrict our further search to the other half of the array. So, accordingly we revise our high and low. So, here if it is less than mid, then we may have to revise the high position, which means we are going to search from beginning till middle minus 1. And if suppose the element is greater than the middle element, we are going to advance, we are going to shift our attention to the second half of the array, and so we revise the value for low as mid plus 1. So, we will be keeping on doing steps 4, 5 and 6 till we reach up till we end up with finding the element, the target element. So, here at step 7 what we do is, if suppose the location is greater than or equal to 0, it means then we have found the element at the particular location. Otherwise, it means that we have not, the target element is nowhere present in the array, and so we report that the element is not found in this array. So, in binary search what we do is, we keep on dividing our array into two halves till we reach up with finding the element, the target element, or at times it may turn out to be negative, that we do not get the we do not find the target element in the array. So, here we have an example. I hope you would better understand the concept of binary search with this example. So, here we have the target as 22, and you can notice here the array is sorted first, and we have set up the values for first and last. Our first is 0, our last is 11. Now, I compute mid is first plus last by 2, so it is 5. So, that is going to be our middle element. Now, I check whether my target is greater than or less than middle. In our case, 22 is greater than the middle element, which is 21 here, and so further search will be restricted to the second half of the array. So, now I have to revise the position of first. Earlier it was 0. Now, I have to revise it as mid plus 1, which is 6. There is no change of course with the last. Now, I recompute the value for mid, which is now going to be 6 plus 11 by 2, which is 8 in our case. Now, I check whether the target is less than or greater than the middle element, which is now 62. 22 is less than 62, thereby now we are going to restrict our attention to the half of this list, which is 22 and 36. This belongs to the lower half of the list, right. So, we move here. Now, the thing is that we have to revise, as we are going to restrict our search to the left half of the list, we have to revise the position of last now. There is no change in the first, which you could notice here. I revised last to be mid minus 1. Our mid was earlier 8. So, now last is mid minus 1, which is 7. Now, we recompute mid, which is first plus last by 2, thereby we get this 6. Now, we compare our target with the element found at 6. In our case, it is a perfect match, and so we report the location of the target element as 6, and we put an end to the search operation. So, here it is even more clear with respect to calculation I have given here. We have an array which is sorted. We have fixed up low and high to be the beginning and end of the array, and we compute mid as low plus high by 2, which is 0 plus 7 by 2, which is 3, and our target is 6. This is how we start. This is during the first iteration, and we now check the mid is 3. We check the middle element, which is 7. Our target is 6. So in our case, our target is less than the middle element, so we have to restrict our further search to the lower half of the list. We have to revise the value for high now. High is actually middle minus 1. So now I compute mid now. High is 2, low is 0. So 0 plus 2 by 2, which is 1. So now we check the value at 1, right, and our target is 6. Thereby now we again do the third iteration with checking whether target is equivalent to array of mid. In our case it is so, and so finally we report that the element is found. So this is how we do step by step, how we do binary search step by step. And here I have given you an example to make you understand how binary search could turn out to be unsuccessful. In this example, you could see we have our target as 11. You could see that initially the array is sorted, and our low is 0, our high is 11, and we compute mid, which is 5 here. I compare target and middle position, which is 11 and 11 is less than 21. So we have to restrict our attention to the lower half of the list. I revise high to be mid minus 1. So here in our case it is last to be mid minus 1, which is 4, right, and our first is left unchanged. Now we compute mid again, which is 2. Now we check the element at the second position, which is 8, and compare that with the target. In our case 11 is greater than 8. So we have to move to the upper half of the array left, which is 10 and 14. So when we shift to upper half, we have to revise the value for first. It should be mid plus 1. Our mid was 2 earlier. Now I have reset first to be mid plus 1, which is 3. Now we compute the value for mid again, which is first plus last by 2. So it is 3 plus 4 by 2, 7 by 2 is 3 actually. That is our mid element. So mid element is 10 now. We check whether the element 10 is greater or less than 11. So in our case our target is actually greater than 10, no. So we have to move to the upper half. We are left with only one element, which is 14. Now we compare 14 and 11, they don't match. So this is going to be the end of binary search with respect to this particular example, and so we report that the target element is not found in that list. Had it been a successful search, then we should have here our target should have been mapped to the condition mid equal to target. If that matches, then we will be reporting the search to be successful and reporting the index as the result. In this case, it has turned out to be unsuccessful, and so we say that the element is not found in this array. So this is the algorithm for binary search. Of course, we have already learnt it clearly. So the reason why I have added up here is that binary search is actually an it's an algorithm that falls under the category of divide and conquer. I hope in the very first lecture I told you the different algorithmic approaches, and divide and conquer is one such approach. Here what we do is we keep on dividing the search space by 2 every time, and that drastically reduces the time complexity of doing a binary search, and that is the advantage we gain over the concept of with binary search, just because of the concept of divide and conquer here. And when we talk of the best, average and worst case complexities of binary search, as I said before, if suppose the element which I am looking for is available at the first position, say in case of binary search during the first iteration we compute the middle element. If suppose that is the element which we are looking for, then the search would just get completed in making one comparison, right. So, that should be my best case, which is order of 1. In all other cases, be it average or worst, it is going to be order of log n, just because every time the number of comparisons get reduced by half. And I hope by this time you remember the complexity classes which we learnt earlier. I told you that one is the lowest complexity class, and algorithms whose time complexity is less or constant, we say that it falls under that category. The next is log n, which means it is slightly less than n, where n represents the number of elements, right. So, here just because every time the search space is reduced to half, we say that the average and the worst case complexity of binary search is log n. So, having learnt the two kinds of searching, namely linear and binary search, now we move on to sorting. Sorting is putting something unordered into an ordered one. So, here you could see here in this example, we have some 6 elements, and you could see that all of them are not in any order, and this is what we expect in sorting. We have placed them in ascending order. So, order could be either ascending or descending, but we want to enforce some ordering of elements within that array, and sorting helps to achieve that. And we have plenty of algorithms actually for doing sorting, and in this with respect to our syllabus, as we have bubble sort, which is the simplest of all the sorting algorithms, I am explaining the concept of bubble sort here. So, here with the bubble sort, what we do is we partition the list into two halves first. One half is said to be sorted and other half is said to be unsorted. We are going to achieve bubble sort in several iterations. Why it got the name as bubble sort is that either the smallest element or the largest element will try to bubble up and occupy its respective positions during every iteration, and so we call it by the name bubble sort. Here in this example, what I have shown is that we have n number of elements. What we do is that during the first iteration, we start our scan from the end of the array. I compare the last element and the last but one element to check whether the element at the successive position is smaller than the element at the preceding position. If so, I move the smallest element one position up downwards, and I move the highest element by one position upwards. That is, the elements at these two positions will have a swap. And if suppose they are already in order, which means the highest is at the upward position and lowest is in the downward position, then we do not make a swap. So, likewise we will be doing for every pair of positions in this array till we reach the first position. So, as we complete the first iteration in the bubble sort, we claim that the smallest element has occupied the first position in that list, and after that we will be moving this wall one step forward, which means the element left to the wall are all sorted and the elements that are to the right of the wall are all unsorted, and we may have to repeat as many iterations till all these elements from the unsorted segment move to the sorted segment. This is how we do a bubble sort. So, here we have a simple example. I have given 6 elements here. This is part of the original array. All of them are unsorted. As I said before, we do a bubbling up operation from end to first, and as a result you could see that the first element has occupied 8 has occupied its correct position in that array, and so we put a wall here to indicate that whatever that appears to the left of this wall is sorted, and whatever that appears to the right of the wall remain unsorted. And after the second pass, you could see that 23 has occupied its right position. So, you could see the wall has advanced by one position, which marks sorted and unsorted lists. So, likewise you could see that every time the wall gets advanced by one position, and as I have n 6 elements here, my n is 6, and ultimately in n minus 1 passes or n minus 1 iterations, the entire list will get sorted. So, in this case you could see after the fourth pass itself the array has get sorted, and so we stop there. We have not shown the next step here. So, this is the algorithm behind bubble sort. We traverse a collection of elements, that is we move from front to end. So, this is the other way of doing. Earlier we were starting the operation from the last element of the array, or in other terms we can even do the same thing from the start of that array. Now, we see here an example where we do bubbling up operation from the first to the last. So, every time I make a pairwise comparison, and if it violates my condition, I do a swap, else I leave it as such. So, here my expectation is that I want the least element to be available at the first position and the greatest element to be available at the last position in that array. So, every time I make a pairwise comparison, I check whether the element at the first position is greater than the element at the second position. If so, I do a swap. If not, I ignore. That is how I proceed with the rest of the iterations. So, we will see that in detail in the following slides. So, I make a check of 42 and 72. So, here initially 77 was in my first position and 42 in the second position. I compare them and I make a pairwise comparison. As such, since 42 is less than 77, I move 42 to the first position in this list. So, here we do that swap. Next, I compare 35 and 77, I do a swap. Next, I compare 12 and 77. So, again there is 12 is less than 77. So, I advance or swap. Then I check 77 and 101, which means they are already in order. So, there is no need to swap, and then I compare 5 and 101, and so since 5 is less than 101, I do a swap there. So, as such you could see that by the time I complete one scan from left to right, that is the first element till the last element in that array, you could see that we had been doing bubbling, and we have been successful in putting the largest element at the last position in the array. So, as such this array has 6 elements, and as I said before, we may have to repeat another n minus 1 iterations to put all the elements in this array to be sorted. So, here the largest value is correctly placed in that array now. So, this is the algorithm for bubble sort. First we have set up a variable index to be 1 and the last compared variable to be n minus 1, and we have a loop here, and here we have to exit this loop only if index is greater than last compared. So, here our index is 1 when we start this algorithm. When we exceed n minus 1, then we may have to exit that loop, right. And every time otherwise what we do is we check every element at index plus 1 and element at index. If the element at index is greater than index plus 1, then we may have to do a swap, otherwise we ignore. So, that is what we have written here, and every time we after doing this comparison we advance by one position, and so it is index equal to index plus 1. So, we will be repeating it n number of times to put all the elements in a sorted manner. And so, what we have seen here is an example of what we do with every pass from left to right or every scan from left to right. Now, we have a question, how many times should I have to repeat this scan? So, if suppose we have n elements, as I said before, we may have to do this bubbling up operation n minus 1 times to put all the elements in that array to be sorted. So, that is what we have shown here. As such, we have 6 elements here, and of course, you could see that in n minus 1 iterations we have kept the entire list sorted. There is one more advantage, one more thing which we can do to make this bubble sort algorithm work better. So as soon as I put the last element, so during the first iteration, you know, the largest value would occupy its correct position, and so what we can say is that for further iterations I can leave this last position and I can make comparisons till the last but one position. That is how, that is what we have shown highlighted here. As soon as we have kept, I mean, placed two elements in the appropriate position, then we will be restricting our attention only to the rest of the positions in that array. Thereby you could see that every time our comparisons will get reduced by 1 in during every iteration. So we can have a condition similar to this way. So here what we see is that on the nth bubble up we may have to do max minus n comparisons. So here our max is 6 just because we have 6 elements. So at this time what we have done is, so far we have put 3 elements in its place. So what we are going to do is the fourth bubble up operation. So here the formula is that at this point we will be having max minus n comparisons. Our max is 6 and this is our fourth bubble up operation. So 6 minus 4 is 2, and that is why we say that we have only 2 more comparisons to make between 1 and 2 and between 2 and 3. That is what we have shown here with this example. So we have added that particular step in that algorithm, I mean the algorithm for bubble sort, which we have seen earlier. So the rest of the things are one and the same. So here we have a variable named to do, which is set to n minus 1 initially, which is actually the number of comparisons which we have to make. That is what indicated by the variable to do. So we have to exit if to do is has reached 0, and index as such it is set to 1 initially, and this step is one and the same which we did before. We compare element at I and I plus 1. If element at I is greater, we do a swap. That thing is same. Here the only thing is that every time I revise to do by to do minus 1, thereby we reduce the number of comparisons made with successive iterations of bubble sort. So this is actually a refinement which we make with bubble sort. So having learnt the 3 algorithms, one for bubble sort, doing a sorting operation with bubble sort, one for doing searching with linear search, and other for searching with the binary search. Now let us check how much we have understood the concepts which we have learned before with certain questions. First is, what is the time complexity of linear search in the best, average and worst cases? As such, you know, we in a linear search, given a target element, we have to start our scan from beginning till end, right. So the best case would be that we find the element to be searched, that is the target element at the first position in that array. In that case our order of complexity would be order of 1. In all other cases we may have to make that many comparisons. Average case would be finding the target element somewhere in the middle of the array, and worst case would be either finding the target element at the last position in that array, or the element is nowhere found in that list. Even if the element is not in the array, we will be searching from beginning till end, right. So in that case our worst and average case would be order of n. And the second question is, when would you prefer linear search over other search algorithms like binary search? So as such, linear search can be applied to an array which is either sorted or unsorted. So if suppose our array is unsorted, then we can go with doing a linear search, and then if suppose the element to be searched is few, and if suppose our array size itself is small, then in that such cases it is preferable to have a linear search than binary search. And the third question is, what are the preconditions for binary search to work correctly? We learnt already that whenever we initiate a binary search, it is necessary or it is mandatory to have the array sorted. So that is the precondition. The fourth question is, what is the time complexity of binary search in best, average and worst cases? The advantage of binary search is that it reduces the search space by half every time, and when we talk of best case, it should be order of 1, that is the first time we compute the middle element, that happens to be our target element, then that is our best case, which is order of 1. In terms of average and worst cases, as I said before, with binary search, every time the search space is getting halved, so it should be order of log n. The next question is bubble sort a stable sort? Yes, of course, it is a stable sort. It preserves the order of elements in that array, and so we say that bubble sort to be a stable sort. So, to summarize what we have seen so far, we have learnt one of the simplest sorting algorithms, namely bubble sort. As such, if we have to sort n number of elements in a bubble sort, you may have to repeat n minus 1 iterations. At every iteration, we claim that one element occupies its correct position in that list, and we call that operation as bubbling up, which means we do a pairwise comparison, and if required we will do a swap, that makes up a bubbling up operation, and during every iteration one element from that array would occupy its right position in that list. And for n elements to get sorted, we may have to repeat that procedure a maximum of n minus 1 times. And of course, there are plenty of other algorithms, sorting algorithms, which usually take time less than this bubble sort, and we have linear search where we can do, we can make a search to find the target element in that array even if the array is sorted or unsorted. And we learnt about binary search algorithm where we can do, we can search for an element even if the array is, we can search for an element only if the array is sorted. So, now we have learnt all the operations as a part of array, namely how to access, how to traverse, how to insert, delete, how to do search and sort operations, and all these operations make up arrays ADT. And in the next lecture, we will be moving on to the next linear data structure, namely linked list, and hope you might have understand the concepts of array and all its operations, and thank you for watching.